Okay. Hello, everyone. Welcome to the next meetup organized by quantum computing groups from Washington, D.C., Toronto, and Warsaw. My name is Pavel, and I will be a moderator today. And today we have pleasure to host our great speaker, Dr. Saumya Biswas, and he will give a talk titled Geometric Machine Learning with Symmetries and Graphs, Applications in Molecular Problems. Before we start, we would like to just announce that, so first of all, this meeting and this talk is recorded, so we'll later upload the video to our YouTube channel if there are no technical issues, of course. And we've agreed that this talk will be interactive, so if you have any questions, please raise your hand and will try to ask your question during the talk, or you can also post your question on the chat, and we can also try to ask it when there is time for this. So at the end, there will be also a dedicated Q&A session. So we'll also have time for discussions. And we would also like to announce the next Washington Quantum Computing Group meetups. So tomorrow, Professor Snehal Lata will give a talk about blockchain in the quantum area, risk, opportunities, and the future of secure decentralized systems. Then on February 7th, Dr. Xu will tell about symmetry, topology, and magnetoelectric multiferrocity, ferroelectric tweezers for quantum magnetism in hexagonal ferrites. And then on February 8th, I'll be the moderator again, and Dr. Jarek Duda from Jagiellonian University will tell about biology-inspired neural networks with multidirectional propagation of values and distributions. And then on February 21st, Terry Bollinger will give a talk about an easy intro to Feynman's quantum electrodynamics. Then at the end of February, Professor Shafiqul Hai will give a talk about the design of a quantum photonic full adder gate based on an 8-mode integrated optical circuit. So I will be the moderator again. And finally, on March 8th, Lynn Barron will try to answer the question, what is space density from medium ontology to the space-time constant K? And Helen will be the moderator. And again, on March 21st, Terry Bollinger will give another talk about a dual universe model of reality. And then on April 18, Terry will continue and will give a talk about foundations of localized symmetry mathematics. All right, so we hope that you will also join our next meetups, but now I'll stop sharing my slides. And Saumya, if you are ready, the Zoom is yours.
Yeah.
And first of all, thanks for accepting our invitation and thanks for giving this talk.
Thank you very much for inviting me. It's really an honor. It's also very exciting to be giving this talk. Double checking, you can see my screen now?
I can see it, yes.
Okay, so I hope that the talk is interactive. So please help me out if I don't see like any raised hands, and so that I can address the questions. Once again, thanks for inviting me. And this is going to be kind of like an idea level talk. And I'm going to talk about a few different disciplines, and it would basically go from sometimes physics to computer science to maybe some mathematics, not much, and then some chemistry too. So maybe that's why you should have come. I mean, that's the reason you want to hear my talk out. I saw some distinguished gentlemen and in the audience too. So it is also possible that you know too much about this, and then you'll not have a lot of fun. But other than that, this is an application level talk. Like I will be talking about methods that worked if you are a machine learning engineer and maybe you are playing around with quantum machine learning or even any kind of machine learning, classical machine learning, a lot of the time it happens that you struggle for the model to learn. And then it becomes a question of trying new ideas. Like um, if you change the architecture, or if you change some sort of, you can find a trick that captures the property of the data and makes it trainable, because of course there are complexity theorists working on very important questions and problems. But first, what you want to do is to find a way to train your model. It becomes a challenge. Now there are very different buzzwords in the field of quantum machine learning, like barren plateaus. A lot of the time we struggle for a model to train. This is why I kind of like focus a little bit on generalizability. Like, okay, so maybe the method succeeded in something, and how can we increase its chances of generalizing, maybe on an unseen data, maybe on some sort of a different feature of the data. And the method focuses on that, mostly application level. And I really hope that I can tell you something interesting, something new today. So it's a very generalized title, like geometric machine learning. And as I'm soon going to talk about it, even if you are not paying attention to the geometric aspect of it, quantum machine learning or quantum computing in general is basically geometric, or you cannot simply ignore the geometric aspects of this problem. So I will talk about two datasets. Now I'm kind of like giving you an overview of these datasets. I was trying to contemplate the question, like, what if quantum machine learning, what are the deterrences, what are the challenges for quantum machine learning to become like an industrial reality today? Maybe like one of the biggest reasons is that we don't have a lot of qubits yet, and also it's expensive. If you're going to run it iteratively, then for into this NISQ era, this is quite expensive. If you want to use a simulator, that's what I'm doing, maybe Qiskit from IBM or Pennyline from Xanadu, then I guess you can go as high as 9 qubits or 16 qubits on Qiskit. But it tells you that quantum machine learning still has a challenge in reaching the data intensive problems. So what problems should we try? There are robotics problems. Then you can start with some sort of 3D point cloud data, a massive amount of data, and how to encode that becomes a challenge. Or you can start with genomics data. That's also a very big problem, or a very interesting problem in classical machine learning. But I chose molecular problems because, of course, then there is a lot of literature and a lot of knowledge about the symmetry groups and the structure of molecules. So if we know how these molecules can be tackled, like the paper I'm going to talk about tackles two molecules. One is lithium hydride, the other is ammonia NH3. This might tell us how we can gradually tackle on further complicated or more data intensive problems. So like the dataset I will work on was created by a quantum chemistry software. So if you have gone to enough talks, you might have heard of this quantum chemistry software, DFT software. Like this one was created with SHI-4, PSI-4. There are many of them, Gaussian and many others. And what I did is called the Hartree-Fock simulation and created these data sets. So these are the features of the data. And from that, you can kind of like create some derivative quantities. If you know the position of two atoms, you can calculate the distances. And this data come with like geometric information, like the coordinates, the 3D positioning and everything. So this is for ammonia, NH3. And I want to answer the question on an application level, when or how can we have like a well-structured quantum machine learning line of attack to train on this ammonia molecule? Then let's just quickly go over quantum variational learning models. Like I suspect everyone is familiar with it, but just for completeness, just in case an undergrad is also listening. So of course, we have something very similar to what we do in classical machine learning. And okay, I was looking for the cursor, but I mean, my cursor would have to do. Please follow my cursor as I go through the next, the remaining part of the talk. And if you can't see it, please let me know. So of course, what we try to do in quantum machine learning is form a parametrized circuit and form a wave function that depends on this circuit, psi of theta, theta being the parameters, starting from some fiduciary state psi naught. And then we try to calculate features like it could be expectation value of something, like some operator. Writing it out like this means expectation value in quantum mechanics. And everything is similar. What the exact things you would do, like calculate maybe the derivative. And some people can also calculate Hessians, but the ideas are the same. You have certain formulas that enables you to calculate derivatives and stuff so that you can calculate your cost functions and iteratively improve. Now, let's talk about data encoding a little bit. So quantum machine learning means you want to give two kinds of numbers you want to feed to your quantum machine learning. One are some parameters that you would optimize for. The others are the data you got from like the data set you're training for. So how can you represent, how can you feed your data or encode your data into the quantum states? There are a few options. The most two common or basic ones are angle encoding and amplitude encoding. So my cursor is on the angle encoding now. This is a little wasteful in terms of qubits. So if you have 10 numbers to encode, you're going to need 10 qubits. Qubits can be rotated on something. I will get to there soon. And if you just make the angle of rotation proportional to the data point, then on one qubit, you can just encode one number. So this is kind of wasteful. So 10 numbers can only go to 10 qubits. And then there's the option of exponential growth of the Hilbert space. So if you have like 5 basis space, you have 2 to the power 5 coefficients or amplitudes. And that could be like an advantageous thing. Amplitude encoding means now if you have 100 numbers, you are going to need log 100, a much smaller number of qubits to represent it. But it becomes a little difficult to like encode a lot of numbers. So that can be a little challenging. We have to kind of like deal with some sort of trade-off, like maybe 100 numbers are fine. So angle and amplitude, these two are really how we would encode our numbers. Now, there is a question of symmetry. Like a lot of data could have no symmetry at all, but now let me introduce you to the actual problem or actual theory I'm trying out for this talk and the paper I talked about. There are many good papers on it. I recommend like Johannes Mayer's paper, PRX Quantum, a few years ago, 2 years ago, I think. They did a very good summary of the things. And sorry, did I hear something? Trying out for this doc and the paper I talked about. There are many good papers on it. I recommend like Johannes Mayer's paper, PRX Quantum, a few years ago, 2 years ago, I think.
George, can you maybe repeat? I'm not sure if Dr. Pisvas has heard your question.
I thought it was an echo.
Maybe. But I know that George was unmuted for a while, but I'm not sure if he wanted to ask a question. Okay, I think maybe we can continue.
Okay, so please follow my cursor. So we try to figure out for some label y that we decide from like wave functions and expectation values of some observable. There are two kinds of numbers we feed. One are our data set, and the second is some parameters. And there is a question of embedding. So let me take my cursor over this. Embedding is necessarily a unitary transformation. So the only thing we can do on a quantum computer is unitary transformations. Like all gates are unitary, of course. That's the only physically reliable or physically, realizable gate or operation. Would our choice of embedding have a significant effect um, on our restricted space that we are trying to study? So now I will go to the specific embedding that works very well for some reasons. And second, this paper emphasizes that your data could have some symmetry. The example could be you have a molecular data that came with special coordinates. It could be ammonia, and you have maybe nitrogen is at the center, and you have the coordinates of the 3 hydrogen atoms. So this came with a symmetry, and these are 3D numbers. The way we look around our world, look at the room we are sitting in, and define the positions of every object. So if it comes from a 3D geometrical data, would it have a bearing on the space we're working in? So the method I'm going to use, taken from that paper, looks something like this. And I'll try to retroactively come back and try to tell you why the geometrical nature of the data, whether you had 3D coordinates or not, actually makes a big difference. So you are going to use alternate layers of, it's called re-uploading. Quantum machine learning folks are very familiar with this. You're going to use alternating layers of unitaries, like one, I'm calling it UG, the other UN. So in alternating layers, one of them you'll feed the data, the other in the parameters. And the specific encoding that works very well looks like this: e to the power minus I, your 3 Pauli matrices weighted by 3 classical numbers. Now, this could be the coordinates you have. And soon I'm going to show you how this gives it some sort of equivariance property. First, before that, I should also tell you what equivariance means. But in effect, the answer we want to use is in equation 1. We are alternating those layers N and G repeatedly. And we have to do that because of the no cloning theorem. We have to reapply or re-upload our classical data into the state that we prepared. So this is from that paper, or this is what people do when they're trying to build the equivariant neural networks. Now, there are 2 parts to it, of course. Like if we are going to go to these equivariant networks, what kind of states should we choose? Should the states have some sort of symmetry? And second, what kind of operators can we choose? Must operators also be restricted to certain type? When I was talking about the encoding operation U of X, maybe that needs some sort of restriction. So we have to talk about symmetry in both of them, states and operators. And then first, I will tell you what these 2 ideas, one is invariance and equivariance, is on a mathematical level. This might not make complete sense, but soon I'm going to show you with a diagram too. That probably will make it easier. So first, on top, I have symmetry invariant prediction or data labeling. So invariant means that you did a transformation, but of course it maps back to the original, where the state or the label or the prediction you started with, you did a transformation, it must get back to the original transformation. It's a very strict requirement. But when we are talking about equivariance, then we kind of relax the condition. And if you can see, U of VSX is not necessarily U of X. There is it's modulo a transformation. So like US dagger can, in fact, it is okay to be equal modulo that operation. Okay, now this is a little hard to explain here, and I will probably be able to explain to you completely soon. But before that, like, I will tell you something about my quantum journey, and I'm going to talk about fundamental particles a little bit. So, the famous book by Stephen Hawking came out a long time ago, and I was reading it as a high school student, I think. And I remember reading this passage, which at the time did not make any sense to me. So first, you can have like a ace card, and if you rotate it by like 360 degrees, or if you rotate anything by 360 degrees, it maps back to itself, right? And you can have like a double-headed arrow, or the queen card you can see here, and you only have to rotate it by 180 degrees for it to map back to itself. So that would be spin 2. It is very easy to kind of like envision spin 1 and spin 2, because we are talking about rotations of 360 degrees or higher. And what he writes about spin half is that you have to rotate the object 720 degrees before it could map back to itself. So at the time, I was a high school student, and it made no sense to me, because if I looked around, every object I could see, they would all map back to itself under 360 degrees of rotation. It is not possible that it would require 720 degrees. But later I had of my formal education, like, of course, I took everything, quantum mechanics, quantum field theory, a bunch of courses. So maybe you have seen the prop on the left. You have like an outer sphere, and you have an inner sphere. We move a particle on the outer sphere and move another point on the inner sphere by an angle that is half the angle that moves on the outer sphere. So a prop like this, what it does is, if you rotate the outer particle or particle on the outer sphere by the whole 360 degrees, and it gets back to the original point P, on the inner circle, it only traverses half of it, because of course we defined the inner circle movement to be half of it, and it only goes to the south pole. So mathematically, this object is called a spinor, and maybe it predates the ideas of spin and quantum mechanics, everything. But a spinor is defined when you have a mathematical object or mathematical function that goes to negative of its value as you change its argument by 2 pi. I hope you can see my cursor. And then you can take any number you have in your 3D space, and you can use the spinors to like write it out on your SG2 sphere. So when we are talking about qubits, we use our SG2 spheres. You can take a point in your 3D space. If you know it's a spherical coordinate systems, then you can form the operator sigma, and you can calculate the eigenvalues, which most people know. Like if you have done some quantum mechanics, this is like cosine theta over 2, sine theta over 2. And you can plot that on the block sphere. So there is a mapping of taking any 3D point you have in mind and putting it on a block sphere. So this is about spin half particles, or this is part of the wave function of a fermion, and I want to come back to that later. Then some interesting things, something I find very interesting. Oh, actually, I have already discussed this part of it. If you know the coordinates of any object in the room you're sitting in, or some coordinate axis in 3D space, you can write it out on something called SO3 linear algebra. So SO3 is a group. I'll talk about groups soon, but SO3 is a group of all rotations about the center of a sphere. And if you can write it out as equation 1, so if you can find out the polar angle and azimuthal angle, then those theta and phi unambiguously lets you write it out on the SU2 sphere. So this is really for the uninitiated. Like if you are maybe like a hardcore computer scientist or computer science student, haven't really looked into physics too much, it's like if you know the position on a sphere, if you know the polar and azimuthal angle, the eigenvector of the sigma operator gives you its position on the SU2 sphere. So there is a one-to-one mapping when you are talking about a Lie algebra mapping from SO3 to SO2, which means the space we live in, basically SO3, you can map it exactly to SU2 on a qubit space. There is a local isomorphism. And I will also tell you about Lie group in a bit, where it gets a little complicated, but the idea more or less holds. Like you kind of have an one-to-one mapping. You can take one and you plot it onto the other. So maybe this is a good time to tell you about the Lie group. Please look at the left-hand side of the things. Like these are the gates. Maybe even if you're in computer science, you have seen what the gates are. An x gate is Rx. It is of the form e to the power minus I theta. Theta is the angle you want to move it by. Then x. So in physics, we will call the ones in the exponent, like this x, y, z, to be the generators or the Lie algebra. And the ones that come out on the left, or the complete quantity, to be the Lie group. And I mean, the representation of the Lie group. So please look at these matrices, 2 by 2 matrices. It's like if you can have the same algebra or with some matrices, then it is called a representation of that Lie group. But what I'm just covering here is if you just want to rotate a qubit by, let's say, about the x-axis by 90 degrees, you just put the x operator on the exponent, you take the 90 degrees, and e to the power minus I actually gives you that rotation. And if you want to calculate or go via the mathematical route, then Lie groups are kind of like the derivatives of those curved spaces. And if you take the derivative, then you go to the Lie algebra. If you take the exponentiation, then you go to the Lie group. You can go from one to the other. So quantum computing or qubits inherently has this affinity or has this connection with geometry. If you are doing some sort of algebra, maybe how a mathematician does, 0 plus 1 is 1, 1 plus 1 is, depending on the algebra you do, 0 or 2. It is different from that. All the gates you're doing is rotations. And if you do two gates together, it's one rotation after another. There is a geometric aspect to it. So that was the definition of Lie group. But so far, I was just trying to tell you that whenever we are working with qubit, that has a very close relationship with the way we rotate objects in 3D. Now, I would talk about a visual representation of what the idea of equivariance is. I told you about in terms of like mathematical operations, which is not always very easy to follow, but I hope this example makes it very simple. So first, you have the graph on the left, and I define a reading system, which is the way I would read a book. So I would go to all the rows, like first I would go the first row and read from left to right. So when I read the graph on the left, I would read first row, left to right, 5, 3, then second row, 1, then third row, 4, 2. And this is the sequence I wrote out in row number 2, 5, 3, 1, 4, 2, going from left to right the way I read a book. This is how a graph is defined, means you have some vertices and you have some indices. Now, there is a famous problem that is called like relabeling isomorphism, which is if you permute the vertices of a graph, it does not change the graph. Physically, it's the same graph after the permutation. And it creates some sort of problems when you are doing quantum machine learning, but that comes after this. First, let's see like an example of an equivariant function, which is A. If I multiplied all of these vector elements by a constant number, and what do I get? In this vector, every number 5, 3, 1, 4, C is padded by the number C because I multiplied by a constant number. So I will do the same to the right-hand side. Now I have a different sequence. like if I read it with the convention I defined, first row 1, second row left to right 3, 4, third row left to right 2, 5. So 1, 3, 4, 2, 5. Then I get 1C, 3C, 4C, 2C, 5C. And you can see that the two sequences I got are actually not the same. But we call it a equivariant function because if I get back the same numbers, it is possible to permute it back to the original sequence, which is 5, 3, 1, 4, 2. For equivariance, it is enough to get back the same numbers. You don't have to get back them in the same order. If it comes back modulo a permutation or modulo a symmetry operation, and let me say that again, if it comes back modulo a symmetry operation, then that's good enough. That's good enough for equivariance. We call these functions equivariance. So the function f of x times c is an equivariant function. This is not good enough for an invariance because invariance, you must bring it back to the actual same order. That function x times c is not an invariant mapping. But a possible invariant mapping is the sum of all the numbers because then the permutation does not matter. Before and after the permutation, you get the same summation, 5 plus 3 plus 1, you get 15, both before and after. So example of an invariant function is summation of all the numbers. Now, saying this out again, actually I explained it in the last slide. Maybe I should have showed you this graphic. For equivariance, a different order of the numbers is good enough. Like after permutation, we get something like 1, 3, 4, 2, 5. Now I have written them as columns, not rows. This is the same as the original column, modulo a permutation, modulo p. And this is good enough for an equivariant operation. Now what I will use a lot for the remainder of the talk is the two equations at the bottom. So if you can, my cursor is on the operator p pi now. If I make it identity 1 or if it drops off, then that would be the condition for invariance, which means after the permutation happening on A, the state must come back to the original one. And just like you can see that it is good enough to get back the same numbers modulo a permutation operation, that permutation operation can be there. So what we have on the right side of the screen, the diagram, actually satisfies the equation on the bottom. This is the condition for equivariance. And you really should tell me if I made a mess in explaining this, but because this is important. For the remainder of the talk, I'm going to deal with states and networks where I'm going to try to enforce this condition, whether it is permutation equivalent or not. And I also showed you like the paper I'm following a lot. And I will once again mention it, and the authors and everybody, they went through all the mathematical proof that you have to do to actually show that condition, that they were using an equivariant neural network. You have to show this condition. It is more relaxed than the invariant condition, like getting the state back modulo a symmetry operation, in this case, permutational symmetry. So putting it in a succinct form, we have to think about two things, of course. One is like states, one is operators, that I was also trying to emphasize before, because as you do this quantum computation work, quantum machine learning, or even just quantum simulation, you have to think about two things, of course, the state and the operators. So the definition of permutation invariance on the states is top left, where my cursor is right now. I'm sorry, that was the invariance one on the left-hand side. And on the right-hand side, where you would need an extra permutation operator or an extra symmetry operator to bring it back to the original state, is the invariance operator. So that is for the state. You can also think of what kind of restriction you would need on the parametrized quantum network you are sending it through. And if you just work it out, like it's a little more involved doing it in the Heisenberg picture on the operators. On the states, it's like, I mean, math wise, it's like more obvious, but it comes out something like this: U theta and UG has to commute. It it is like the generators of the symmetry would have to commute with the layers of quantum network you are sending the state through. Okay, so I hope it makes sense, like what you have to do for equivariance and what you have to do for invariance. And please just ask, this part should be clear enough, or I'm trying to keep this kind of like easy enough or surface level so that we really maybe like get the idea more. Um, so let's talk about permutation symmetry a little bit, because that also becomes important later. The specific um, answer I would use that was taken from the paper I showed before is the one on top row on the right. There are many parameters. I hope you still remember the UN unitary operations and UG unitary operations, which are applied like alternately. And I hope that you have some familiarity with the permutation operation, which is like you have a state, some sort of tensor basis, I1, I2 through In. And after permutation, they just become, one becomes sigma of 1, 2 becomes sigma of 2, n becomes sigma of n. And I'm going to resort to the idea of permutation operators and a lot. So this is basically what I have to do eventually. Like permutation symmetry solves a lot of the problems I was trying to do. And I have already talked about group. And just to like, maybe if there is an undergrad here or something, just to like recap, group theory is our way of like categorizing symmetry, because a lot of the time we will work with something that is highly symmetrical. Maybe like the triangle here, it can be rotated by 120 degree and it maps back to itself, right? So when we have something like that, that has operations that map it back to itself, just like I was talking about spin 1, 2.5 from Stephen Hawking's book, fermions have can have a spin half, like electron, a fermion has a spin half. So when you have an object like that, that will map back to itself under some symmetry operation or some geometric operation, we find it very convenient to talk in terms of group theory. Why? Because these things more or less comes from closure. Like here, one operation is rotation by 120 degree. Another operation is rotation by 240 degrees. Now, what would happen if I applied one after the other, 120 degree, then 240 degrees? The combined operation is also part of the same set, which is a 360-degree rotation. It brings it back to the same set. So this closure property, mathematicians found out before, that is very useful. Then we can have a closed set when you can define like a rule of multiplication or rule of composition, where you take two operations, you compose them, and it becomes a third one, not outside the group, but within it. And so I'm sorry, it cannot be seen very clearly, but groups have these conditions. For a set to become a group, it has to be closed, it needs an inverse element, it needs an identity element. But that was the idea I was going to show you there. And then Lie group is defined in terms of sequences of matrices. And the closure property is important here too. Like if you just go through the textbooks on this, you have certain sequences that you define for matrices, and they have to converge to a one that is within the set, meaning it has to be closed. But we can kind of think of them as continuous generalizations of the group. I was talking about 120 degree, 240 degree rotations before, but what if those rotations are continuous? Like what you can do on for a spins for a Bloch sphere of an electron or a spin, then you can rotate it by any continuous degrees, or you can rotate it by 35 degrees, 37 degrees, or any arbitrary number of degrees. It's not discrete. Then it's rather a question of finding the representation, like the polymatrices we know is just the matrices that follow the algebra we need. So these are representations of that group. So simply put, SU2 group or these continuous Lie groups are kind of like generalizations of discrete groups. And one more time, you have Lie algebras that define some sort of commutation relationships. Algebra means you have certain properties, like you have vectors who can have a multiplication by scalars, who can have a product, a strange one called commutator, but eventually you can have some Lie algebra, and if you exponentiate them, you can have the Lie group. So that's just, I was trying to recap what happens here. But now notice something that I, I wonder where I cited it. Notice something that whenever we have a 3D geometry, like it could be data that came with coordinates. In robotics, they work a lot with 3D point cloud data, where you basically have point clouds where you know the 3D coordinates of each point. You can represent them on a SU2 sphere exactly one-to-one. Maybe that has some benefit. Why I'm saying this, soon I'll show you in a slide, is right now, I hope you're probably aware that equivariant neural networks are also very popular in classical machine learning. Like a lot of the complicated learning tasks, robotics, for example, they are saying, the researchers are saying that equivariant machine learning is succeeding a lot. So if you can map them one-to-one into qubits, then maybe it is possible to just have to translate those problems into qubit language. But before that, let's talk about the poly matrices that we use for spin half particles. And if you are familiar with quantum computing, you know these gates, poly gates X, Y, Z. You probably know the 2x2 structures, the numbers they follow. And they have these properties. Like if you square them, you get identity. And these are the other ones. Like if you take X times Y, that is negative of Y times X, you have IZ. Then I will show you like some sort of a, for the problem we're doing, I will show you some sort of a method of coming up with a complete basis. Let's see what that means. I hope you remember the network I showed you before, alternating layers of UG and UN, and that answer is very successful for some tasks. It was taken by this brilliant paper by Skolik at the bottom, equivariant quantum circuits for learning on weighted graphs. And then they would come up with these ways of writing equivariant networks. But first of all, let's take a problem. Like maybe I have to tell you about commutators first. Physicists are very familiar, but outside physics, maybe not so much. My cursor is on the commutator of A and B. If you have A, B, two operators, the commutator of it is AB minus BA. And if the order doesn't matter, then it becomes zero. AB minus BA is zero. Why that is important is whenever you are writing a permutation unitary matrix, which would be the permutational gate you would apply on a number of qubits, it can always be written in terms of a few swap operators, right? You want to permute 1, 2, 3, 4 to maybe 2, 1, 4, 3. You can always write it as a number of swap operators. I don't know, maybe swap 1 and 3 first, then 2 and 4, then it can always be written in terms of a number of swaps. And swap on a operator level means commutation, like AB minus BA, whether there's zero or not. So the brilliant paper by Skolik, they kind of use that information. And please look at my cursor. Like you can write two bases for two qubits. One is X tensor X, Y tensor Y, Z tensor Z. The second is Z tensor identity, identity tensor Z, Z tensor Z. Okay, so first the punchline. The two sets I'm showing you with three vectors, can form those equivariant ansatz x tensor x, y tensor y, z tensor z. These two sets. You can choose maybe the top set or the bottom set, up to you. What are their properties? For two qubits, all three vectors commute with each other. X tensor x commutes with y tensor y tensor y commutes with z tensor z, and x tensor x with z tensor z. If you can form these number of operators, for two qubits, you are going to get 2 plus 1 or 3 of them. If you can form these operators who all commute with each other, then you can use that in the UN operation you do. I'll show it later. But your first task is to find this uh, basis where you have all members commuting with each other. People familiar with stabilizer generators, it will kind of like give you that idea, like you are finding some operators that all commute with each other. But if you can remember it a little bit, like x cross s, y cross y, z cross z, this is choice one, or z tensor I tensor z, z tensor z, this is choice two. If you can remember it a little bit, I'll show you soon that again. And why should they commute with each other? Because the permutation is a product of a finite number of these change of order or commutations. So if they commute completely, permuting them would not contribute any signs. And that's like the clue we use. But before that, the other idea I was telling you about a little bit. Unfortunately, I could not change the color of this slide, so you may not be able to see this. But please look at this paper on universal and fault-tolerant quantum computing. I think there are multiple references where they talk about this, but this is one place where they do talk about it. So there is the concept of Euler rotations, and this is not very common knowledge, but you might have seen that in some sort of quantum computing book. You are trying to rotate a qubit state initialized at a certain point with respect to an arbitrary axis. This arbitrary axis is not one of x, y, z, because then the problem is easier. If you want to rotate with respect to the canonical axis, x or y or z, then the default gates we have available in quantum computer, x, y, z gates, they can simply do it. But what if the rotation axis was not aligned with one of the three? So from robotics and from quantum computing, there is this way called Euler rotations, where you can do a series of 3 rotations, one after the other. The most common choice is z, y, z, and you can have many other choices. So you rotate the qubit first with respect to z-axis, then with respect to y-axis, then with respect to z-axis again. And with these 3 canonical rotations, which are available with your XYZ gates, you can implement the rotation with respect to any rotation axis you have, not necessarily the canonical axis. So according to this paper, or I think this is discussed in multiple places, this has a one-to-one relationship when you are working on your 3D space geometry, which is SO3 Lie group, Lie algebra, I should say, and when you are working on qubit space, SU2. So the point I was making before, actually this slide should have been there, is robotics people and a number of other science, machine learning disciplines have found that you can have very well efficient generalizable training when you use these equivariant neural networks. Now, if both the states and the operators can also be represented on a quantum computer with qubits, then maybe it's possible we can translate the whole problem onto a quantum computer, and quantum machine learning can successfully tackle the same problem. Of course, you can think of the obvious deterrent. It's not easy to feed that many numbers into a quantum state, but in principle, that's actually possible. And now let me distinguish between the 2 rotations I'm talking about. So one more time, SO3 is the rotations in our everyday life. It is the Lie algebra of all the rotations about a sphere, about the origin. And we write it with a small letter r. like where my cursor is right now, if you rotate an object by an arbitrary rotation axis, not necessarily one of the three canonical axes, x, y, z, you can do it with the series of three rotations, maybe z, x, z. And because I'm talking about rotations in SO3, I'm writing all of them with small letter r. The same thing can be done on the SU2 block sphere. People in quantum computing, we work on the block sphere all the time. Same thing can be done, but for SU2, I'm using the notation of capital letter R. So an arbitrary rotation with respect to an arbitrary axis would be here RZ, RX, RZ. Now I am using capital R to distinguish it from small r. Small r is for everyday space SO3. Capital R is for qubit space, block sphere, SU2. Now, I hope you remember this UX. Please follow my cursor a little bit. This is the clever choice of unitary operator, the clever choice of encoding that gives you the property on the bottom. So I don't know if you can recognize this yet, but this is the equivariance rotation relation I showed you on slide number 2, 3, or 4 in earlier times. It is easier to, equivariance and invariance relationships are easier to see on the state, but if you are a little bit familiar with working on Heisenberg picture, then you would remember this one. Like back then I just told you, okay, so this is the condition, like where my cursor is, ux, u dagger. If you can have that condition, then your quantum gate sequence is equivariant. You would get the equivariant condition if you can implement this u of x. So this u of x is very clever or important. And this would give you rotational symmetry if you can, rotational equivariance if you can use this. But notice something else too. So we have an equivalence relation, but isn't it a little more interesting? Because this is kind of like a hybrid quantum classical equivalence relationship. We, to prove this, what we do is our original data point is data vector is x. The r we apply on this is small letter r. What would happen if we rotated it in a SO3 Lie algebra on our everyday space, small letter r? And on the right-hand side, the RZ, RX, RZ, and also on the right side, you get, these are capital letter R. Now, these are rotations on your SU2 sphere, which is on the qubit, on the quantum side. So left-hand side of the equation is something like classical, the rotation is classical. Right-hand side is something like quantum, the rotation is quantum. You can show the equivariance relationship, it's kind of like hybrid classical quantum, which I find interesting. But most importantly, this is the prescription you might follow for trying to solve certain problems. So I would say this encoding is kind of like important. This encoding is a brilliant discovery or something. And I'm going to show you how good it works on some data sets or something. If you did this, you will, one, get rotational equivariance like okay, I haven't proved this, but proofs can be found in the relevant literature. You can have the equation on the bottom, the hybrid quantum classical equivariance relationship. If you use this, it gives you actually both like rotational equivariance and permutational equivariance. Permutational is very easy here. What if you moved x1 and x2, you interchanged them? They're within the same argument as summations. So changing their order would not do anything. So permutation is trivially implemented. Later, I'll talk about other kinds of permutation implementation too. Now, the idea one more time, and what I was saying is some sort of a hybrid classical quantum equivalence relationship. And I mean, those of you who know about Lie algebra and Lie group, of course, will have no problem following this. But if you just heard of them today, on the left picture on top, we have SU2 Lie algebra and SO3 Lie algebra. I said that they have a local isomorphism. Isomorphism is the group theory or graph theory word for being the same, essentially. So one group can be written by the other. There is a one-to-one mapping. The other thing I was saying about translating a classical machine learning problem completely into a quantum machine learning problem. And from the Lie algebra, you can also get a Lie group with matrix with exponentiation. Now there is like as you can see, the diagram shows it splits into two, then maps to two other. So there is some subtlety, like they call it the double cover of the Lie group SU2, but don't worry about it. In some sense, it is still possible on the Lie group level that you can still have that one-to-one mapping. So if you have data that have geometrical aspects, like it is some molecular data that comes with coordinate, that came with coordinate. You have ammonia data, and you have the coordinates of the 3 hydrogen atoms. Because geometry is involved, even after the transformation, if you use one of these encodings, like I showed you the encoding e to the power minus I x1 times x plus x2 times x2, if you use one of these equivariant encodings, then you will necessarily get the rotational equivariance. So it is not hard to get the symmetry we want. If the data did not have any symmetry, of course, you cannot exploit equivariance. But a lot of the data that we want to work with comes with the coordinates. And this is also what I think is like the most approachable problems today. Like if you ask me to tackle a robotics task today, like of course robotics learning problems are very complicated, very huge. So which problem I think has the best option of best probability for me to crack? I'm going to choose one that comes with coordinates, that comes with geometry, because there are a few encoding known where I can exploit that equivariance very well. So the results I'm telling you today about are in that paper. So we took data sets generated by Shy4 quantum chemistry software. And if you remember the chart I showed you before, like it gives you a bunch of coordinates, some bond lengths, and energy and force. And energy and force are the things we're trying to predict. And then I tried different kinds of models on this. So first, the e to the power minus I x1x plus x2y, that encoding, that is a rotationally equivalent quantum machine learning model. That is the first model I try on this. And then I will discuss another model is maybe in the next slide. You can put those numbers, the data I got from the Shy4 code, on a graph. And after that, like I mentioned a little while ago, that whenever you have a graph, if you relabel the vertices, it does not lead to a new graph. You get an isomorphic graph. Basically, you get the same graph back. So there is some sort of a permutational invariance in the relabeling of the nodes. So we would put the data we have from Shy4 on a graph. Then we have to decide some things like which numbers would go as edge features, which numbers would go as a node features, and then we'll train it. And I had to like try it many, many times, of course. And the original problem I started with right now, like if you're a machine learning engineer, this is really like the first problem you have. You can try again and again, and unless you pick the right answer or unless you pick the appropriate network, your problem will not be trained. So anyways, this is kind of a success story. I'm showing you the things that worked. On the left-hand side, the physical property of energy and force for ammonia molecule, the predictions for that, and on the right-hand side for lithium hydride. So then the kind of figures of merit I'm really interested in is generalizability. So maybe it works for one data set. Is it generalizing well to an unseen data? And I figured out what parameters or figures of merit to investigate for that. Like there are a few of them. Probably you are familiar with. One is generalizability, like covariance, sigma over mu, like variance, sorry, standard deviation over mean, consistency, stability, range. Maybe you know these numbers or something. And we're going to try 4 different kinds of networks on them. So on the bottom is classical equivariant neural network. For that, I think I used PyTorch, and I gave it a massive number of parameters, 27,000 parameters. So in this case, what I'm trying to do is just solve the problem. I don't care how many parameters it takes. But of course, when I'm working with quantum machine learning or qubits, either Qiskit or PennyLane, then I cannot use that many parameters. And the networks I chose, the rotationally equivariant one, which is the encoding of e to the power minus x1x plus x2y plus x3z, that one had 6 qubits, 6 layers, 80 parameters. I tried one with no equivariance at all, with 48 parameters. And the third one is after I put them on a graph, and that one had 4 qubits and 4 layers, 108 parameters. And then we tried to do the simulation. So first, I'm showing you something that worked. This is the training curves you get for lithium hydride, the 4 different methods. They worked, and at least they got trained. But then I used the k-fold validation. I think I split the data into 5 folds and calculated those figures of merit I just showed you: consistency, then stability, mean. And of course, because I used a very expressive and a massive classical equivariant neural network, in the spider diagram, that's like the upper limit of performance. That pentagon is 100%, and quantum models are aspiring, trying to reach there. So among the 3 quantum machine learning models, the green, the red, and the blue, you see that the blue one does the best work. Like, it gets close to matching those generalizability metrics. And the green and the red, they don't succeed too much. Sometimes succeed, sometimes they don't. So this is something other people have reported too. If you use this rotational equivariance or permutational equivariance, then you have a better chance of succeeding with the training. And in this case, the graph permutational equivariant neural network, the blue one, performs the best. It almost catches up with the classical one. So this is lithium hydride, and it has very very mediocre geometry. Like, you have one lithium atom, one hydrogen atom forming a dumbbell. Not too much geometry involved in this. And then we did it for the ammonia molecule, which is geometrically much richer. And this is what we want to see. If the geometry is richer, of course, the shape of an ammonia molecule, like the 3 hydrogen atoms, kind of like a all around the, the 3 hydrogen all around the nitrogen molecule, then you have a much more geometry to play with. And for the graph permutationally equivariant model, we had to choose which numbers to send to node features and which number to send to edge features. And like, this chart summarizes how we put this on the graph. So the graph one performs the best here, because once you have graph, you can also define the graph permutationally equivalent QML. So you can see the blue on the spider wave, the blue curve almost catches up with the classical equivalent neural network, where we gave it like a massive 27,000 parameters. So the blue one almost has a comparable performance to the classical one. And I want to show you one more time. So graph permutational equivariance with 108 parameters is kind of competing with the classical upper limit of 27,000 parameters. Now that is kind of interesting. Like, with a 27,000 factor, or 270, with a factor of 270 factor reduction in the number of parameters, we can still have a comparable performance. What is the trick here? We can take a system agnostic view. Like, we have parameters and we have some sort of machines, black boxes. It can be classical, it can be quantum. So what it looks like is, if you have the quantum one, if you have the qubits inside the black box, you can have comparable performance with 108 parameters. And if you're using the classical one, you're going to need a lot more, maybe 20, if not 27,000, maybe 2,000. You're going to need a lot more. So this is not quantum advantage or anything, but still, like, it seems like there can be some usefulness in quantum machine learning or quantum computation, that this operates differently. The canonical relationships of the constituents is different, and sometimes it can give you higher performance, better performance, like what is happening here. Now I will just tell you what I learned from this project, because initially I struggled a lot in training these quantum machine learning models. Basically, the predictions were not going well at all for force and energy. Because there is the published paper by Skolik, I started with rotationally equivalent QML, which has parametrical equivalence as well. If you remember that X and Y and Z, they are in a sum end, so their order doesn't matter. It has permissional equivalence a little bit, but I'm still calling it rotationally equivalent QML. Then I put the data on a graph and use a permissionally equivalent quantum machine learning model. And what happened is that model turned out to be the best, the model that has the best generalizability metrics. And the lesson I got from this project is, when you maybe when you're struggling with the learning problem, you just put the data on a graph and it might crack it, because that's exactly what happened in the problem. I could not train a model with a dataset. What I did is put them on a graph and use graph permutational equivariance, and it cracked it. So that's kind of like the take-home message, and I took it to heart. And I'm still working on some molecular data. I will show now. It's hard, a much harder one, and I have not succeeded as much as I've succeeded with this one, like predicting the physical properties, something like force or energy, but I'll tell you about them nonetheless. And why these kind of problems could be interesting. So first, why do this? Why pursue quantum machine learning? One is, this is a different kind of machine. The black box is very different from what we do in classical machine learning. It's not layers of nodes and linear and nonlinear transformations. It's qubits, which are geometrical objects, which are and the gates are rotations on those qubits, followed by some sort of measurement and calculation of some sort of expectation values. The canonical relationships are different. Now, let me introduce you to something called a QM9 dataset. Quantum chemistry people know this a lot. It is available on Kaggle and everywhere. Like machine learning people are familiar with this a lot. And I'm trying to work on this. I'm going to introduce you to a different kind of network. I hope you are interested still to hear about it. Any questions or suggestions are welcome. I'm going to tell you about this. I have not succeeded as much as I have with the other dataset that I generated with Shy4. But after that project, I have taken the lessons to heart and do the same things. Like, you can just predict now. I'm going to put the problem on a graph. I'm going to try to use the permutational equivariance, trying to solve it. The process, it would sound a lot like repetitions of the old one, except I was talking about fundamental particles, right? And we will talk about that again. So what is quantum machine learning? You have these SU2 spheres or qubits who have dramatically different properties than the classical bits you have, zeros and ones. And that makes a huge difference because these are geometric objects. These have their own algebra, like x times y is minus of y times x. Then x squared equals y squared equals all the properties you have of Pauli matrices. So spin half is part of the wave function for fermion, like electrons. And there are other possibilities too. Now, imagine you are just indulging yourself. Okay, so the constituent particles of the universe are fermions and bosons. And there are well-developed theories of Fermionic simulations too. So they call it a model of quantum computation. So spin-based model of quantum computation is the one we have been talking about so far. But there is also such a thing called local fermionic modes, LFM, and a lot of people have worked on it, a lot of great works, who have shown that any spin problem can also be done with these local fermionic modes. And in local fermionic modes can also vice versa be represented by this qubit representation and can be solved on a quantum computer. It goes both ways. But I'm assuming that you are new to physics and you don't know the rules of fermionic behavior or fermionic particles. And I'm going to tell you the same, that certain things succeeded and certain line of attacks was used. But maybe I can go faster, or I can just give an overview, because the ideas are the same. The lessons I learned from the last one, I am using in this project as well. So for fermions, there is a strange property that if you exchange two fermions, you actually get back the same wave function, but it comes with a negative sign. So follow my cursor, please. If you have m fermions, you're going to write it as a composite ket, like a tensor of n0, n1, all through nm minus 1. And if you exchange two of it, then you just get a negative sign. So in physics, it's a common knowledge, but if you're your first time, the aj in line number 2, where my cursor is called an annihilation operator. It is acting on the jth fermion. And jth fermion is a 1, if you see in the middle, in the tensor state. If you act it with the annihilation operator, it is annihilated, it becomes 0. But you have to take the fermion all the way through n0 and j minus 1 till you can reach that jth fermion. Each time you cross n0, n1, n2, you accrue a sign of -1. And there is a prefactor of -1 to the power that sum. And annihilation operator, if you are acting on it, on a side there is no fermion to begin with, it annihilates the state and you just get a 0. So physics people know it very well if you are new to this. So in physics, we have these creation annihilation operators that lets you write these fermionic registers. Like you can create a fermion. There are only two occupation possible. One is 0, one is 1. Either like you have the fermion there or you have no fermions there. More than one fermion is not possible, because you might have heard of Pauli exclusion principle. It tells you that two fermions cannot be on the same seat. And these creation and annihilation operators have anti-commutation properties, which means that AG plus AJ AK plus AK AG equals 0. This is what anti-commutation means. And the third one, if you have this specific one where J and K is the same, then you get a 1 on the right-hand side. So there is a way of using these algebra, and you can have AJ dagger AK, you can have a sequence of operators, something like AJ dagger AK, where my cursor is. Then you can do the computations on them. It's just a lot of algebra, and you have to know these canonical properties. So why am I talking about this? Remember when I was talking about spins, I was talking about the fundamental SU2 spin, how they behave, what their algebra is. Now the idea is we just have a new kind of, call it machine primitive, call it model of quantum computation, fermions, where you can also have these registers where you have 0 and 1 possibility, no fermion or 1 fermion. The mathematical language is a physics language here. It's kind of like very complicated here, the way what you're seeing here. And we, people in physics are quite well familiar with it. And if you are a bona fide computer scientist, very new to physics, I hope this introduction helps you a little bit. So then comes the question that because two fermions always gives you a negative sign each time they exchange, how can you represent them on a quantum computer? This can always be represented on a quantum computer. Like if you have m fermions, only you have to do some sort of clever encoding. And like one possibility is Jordan-Wigner transformation, like at the top of the slide. For that, you have to write like a chain of operators, chain of these poly operators, and you can represent any arbitrary creation and annihilation operators in terms of this chain of operators. Okay, the physicist will get bored here because this is common knowledge, but yeah, still, just in case someone was not familiar. So this is the idea. You have a problem in terms of fermionic creation and annihilation operators. First things first, you have to represent them with Pauli operators. Then you have essentially translated the problem to a quantum computing problem with Pauli operators and with SU2 spins. And then it becomes just a question of doing usual quantum computation. So you have to use the line 2 and 3, the two lines I'm encircling with my cursor. And these are chain operators. So you can probably see like there is a problem. Like if you actually want CJ dagger or something like that, you probably know that there are no 3-qubit or 4-qubit entangling gates, efficient ones today. So it could become a challenge. Like if you have a sequence of 6 operators, 6 Pauli operators, how you would implement a 6 Pauli operators on a quantum computer? But you must have also heard of universal approximation theorems. Like it is always possible to represent them with 2-qubit entangling gates, but they will get really long. But what I'm trying to tell you now is the ones when J and K are different, like we are talking about fermions. I hope the picture is here. We're talking about fermions that are well separated in space. J could be 3, K could be 16. Then an operator like CJ dagger CK needs like 1, 2, 3, 13 Pauli matrices together, a very long operator sequence. So if you have like a lattice of fermions, the computation is very hard. You have to do this chain rule where you gradually accrue Pauli operators as per the arrow I have drawn here. So if J and K are something like 3 and 16, you need like a 10 plus 3. 3 and 16, I think you need like a 12 or 13 Pauli operators chain, a very long chain. It becomes complicated. But this is how fermionic operators are represented on quantum computer. So why I'm showing you this, like there are well-defined models that are of interest to quantum chemistry, interest to people in quantum simulation, where you have a model like this. This is a Fermi-Hubbard model. As you can see, it is written in terms of this creation and annihilation operators. This is called a Hamiltonian. It means that it represents how fermions interact on a lattice and how they will evolve in time following this Hamiltonian. Like this generates the time dynamics. So to simulate that, what you have to do is do the Jordan-Wigner transformation. There are other choices too. And Jordan-Wigner works in a way where you start from one end of the lattice and go over all of them, like in a continuous line. And you keep adding Pauli operators as you go over all of them. If you did it like this, then you can satisfy all the fermionic commutation relationships that is required. Then you can do like a faithful quantum simulation of fermions. And one more time, CJK, CJ Decker CK, is the most complicated when J and K are different and J and K are well separated in along the arrow. But now, if you are measuring some of these observables, that it is possible that after doing the simulation, you can measure the expectation value of CZ against CK. Do you see that it is actually equivalent of measuring the correlations of a multi-body operator? Maybe like a 6 Pauli chain, it is equivalent of measuring the expectation value of a 6 Pauli chain. But then it also like behaves well for us. Then we can possibly learn a lot about the system we are simulating or the system we're trying to learn. 6 body, 8 body expectation values that long will tell you how all these atoms are correlated with each other. And Fermionic simulation can actually give like good information, may have good expressivity or learning ability of the problem. So, anyways, very recently, I think last year, November, this paper came out, Fermionic Born Machines, and they successfully trained the QM9 dataset, the other dataset I'm now working on. So I hope you may have heard of Born machines. It's different from Boltzmann machines, which are a little more popular. Born machines, please look at the QWX here. You are trying, just like Boltzmann machine, you are trying to train this is an unsupervised technique. You're trying to train to emulate a data distribution. So you will have a quantum network that upon measurement will give the same distribution as some data. For Born machines, this measurement statistics will come from Born rule only, means it will come from probability amplitudes only. For Boltzmann machines, like if you actually have worked with Boltzmann machines, there is a dependence on energy. The sampling depends on energy. That's different. For Born machines, the sampling depends on the probability according to the Born rule. So it depends on the quantum probability amplitudes. So this paper successfully trained the QM9 dataset that I'm working on now with the Born machines. And these are well-known names in quantum computation now, like FLO is fermionic linear optics. There are also great papers on it. And just like Gaussian boson sampling is like a big problem in quantum computing today, where a quantum computational advantage is claimed. Similar arguments or similar claims have been made for the fermionic sampling too. Like this apparently also is a quantum advantage problem. Like the sampling problem cannot be simulated classically. There are some papers on that. I think I cite them somewhere. But let me show you what this paper last year November, which came out, is showing. It successfully trains on QM9 data, and that compares with a classical calculation, and also benchmarks it against like restricted Boltzmann machine or other methodologies to confirm or validate the results. And from classical calculation, they could show that the bits have covariance that are diagonal, and off-diagonal pair correlations are low. So quantum machine learning could successfully capture that feature. They got the same kind of covariance matrix that classically was confirmed. And this is what I've been trying to do too. So yeah, I can tell you now that that part succeeded. Like I can also get the same patterns that I can confirm against the classical results. But of course, the more interesting ones would be to actually predict physical operators. Like in the last paper, I predicted energy or force. That is difficult. So far, I have not succeeded. And apparently, I don't see other people have done it either. So quickly, Fermionic Born machine is like a generative model. Classical distributions are represented by measurement statistics of a Fermionic Gaussian state, the thing I was just telling you about. And I hope you remember about SO3, which is like special orthogonal group in 3 dimensions. These are matrices that you see, rotation matrices with determinant 1, real rotation matrices. It can be generalized to n what do you call it, matrix dimensions too. So we are going to do SO2n for this. That theory was developed over there too. Now, I will not show you the exact method. It's like you can take Fermionic operators, then you can, one Fermionic operator maps to 2 Majorana operators, and then you can define a Fermionic parity operator. Basically, if you start with n bits, you get like a 4n dimensional binary measurement for the covariance matrix. these are also from physics, like people who do work with Majorana's or topological quantum computing, you would have seen the first line. You from harmonic operators, you can get Majorana operators from these canonical transformations. If you're brand new, don't worry too much about it. The reason we use these transformations is that it is very difficult to exactly calculate on a classical computer the expectation values of harmonic operators exactly. That's why we do an approximation called Gaussian harmonic Gaussian states, which just means that you ignore higher than two harmonic operators correlations. And on the Majorana basis, there is a very easy way of calculating those expectation values. Something called a Pfaffian. Calculating the expectation values goes through a calculating a Pfaffian of a matrix. So Pfaffian is like if I give you a matrix, there is a formula that you can just simply calculate the Pfaffian. Basically, what I'm telling you is this: we transform to Majorana basis so that we can do this harmonic Gaussian state calculation, very simple calculation that gives an approximate value for the observables you want to use. These expectation values are our features that we want to train against. Now, I hope I have cited that paper. Okay, so there was like a famous paper where they have shown explicitly that if you have something called magic states, I'll tell you about that a little bit. If you have magic states and local harmonic optics operators, LFOs, then you can have the sampling problem that has quantum computational advantage. So maybe you're familiar with this too. There are some tasks that can give us quantum computational advantage over classical computation. These are mostly sampling problems, and it is believed that it has been proven that you cannot do simulate this sampling on a classical computer correctly. That would violate some laws of complexity theory, and it can only be done on a quantum computer. So that mechanism was borrowed by that paper, and I'm also trying to do. You take some magic state and you use this FLOs and you calculate some parity expectation value. So magic state is a state that can give you things that are outside of Clifford or Pauli kind of operators. Uh, if you have something called a magic state, with the help of Pauli operators, you can get to something called non-Clifford gates, which is like a necessity. Like we need non-Clifford gates for some quantum computing task, or universality. So there is something called magic state, and these are the setup I'm using, just like this paper used. So you just have my word to go up on this, but why I am taking on this project and why, I mean, how I'm using what I learned from the last project is really the only important part. Just one more time, what you can do is you can have a harmonic lattice. You can have some Z operators, like where my cursor is, Z string operators, and you can measure their expectation values. These becomes your features for training. And because of the rich physics that's behind it, the techniques that we have for calculating these expectation values are well developed. Like I told you about something called Pfaffian. Like if you have a matrix, you can calculate its Pfaffian readily. It gives you a way of calculating these expectation values on a Gaussian harmonic approximation. So this is just a mathematical machinery for you to calculate the expectation values of some operators you defined, and these operators take values between 0 and 1. And I don't want to bore you too much. Like FLO transformation, this would be interesting to a physicist, but well, if you're a physicist, you're probably familiar anyways. The transformation has this form where you have some orthogonal matrix, just like you have SO2n, and that comes from exponentiation of a matrix A. Now let's just focus on that. Like why I'm telling you this story today is just the last line in this slide. The orthogonal group operator is exponentiation of A. Now, this A matrix, when you form for these Fermionic problems, will come out to be antisymmetric. If you transpose it, it becomes negative. And this gives us a way of representing them on a graph. So let me show you like the forward pass together. We want to take our data, put it on a graph, and then calculate these orthogonal matrices by exponentiating. The matrix A is antisymmetric, and then there is just some mathematical way of calculating the expectation values we want, like covariance matrix, then their expectation values with some mathematical terms like Pfaffian or something. You don't have to worry about that. But the fact that there is this step of exponentiating A could become important for us. Then what I was trying to do, because of the lessons I've learned before, like the lesson I learned before is when a problem becomes hard to train against, what you should do is put it on a graph, and it might actually crack the problem. That's the same thing I'm trying to do here. And I hope you kind of remember the kind of equation you have to satisfy to show equivariance. So easier to see when you have on the state level, but look at the line with the isometrics equivariance. A little harder when you're showing it on the operator level, but because of the exponentiation operator, basically, if you combine line 2 and 3, you can show what you need to show. That line 2, that P, the permission operator matrix A, P permission operator transpose, it becomes like you can have the third line from the second line because of this exponential format. What I'm just trying to tell you is that the mathematical structure the problem has, you can have the permutational equivariance because of line 2 and 3, because that step is in the forward pass. So that was my idea. Okay, so if in fact this can be represented on a graph and have permutational equivariance, maybe we should try to play the same game as I did before. So now this is just like a write-up of what that process looks like. Don't worry about it too much. You take the specific data, you represent them on the graph, and then you try to do the forward pass. And basically what happens is, I did not present the numbers here. What you want to see is like low loss, like well trainability. Eventually the loss is minimized, and then maybe I have the, that's weird. I thought I had the graph somewhere. Okay, maybe I forgot to put the graph, like how the actual code works. And then just like the paper we had before, the paper I actually got introduced to the problem too, we want to make sure that the correlations we measured are not hallucinated, or they are the same ones that if I did a classical calculation on the numbers, that it will match with that. And unfortunately, I think I forgot to put that slide in. This method is validated against that it can be trained. First, it can be trained was shown in the paper I showed you anyways, but I took a different form, different path. Like I am taking the Fermionic parity operators, putting them on graph, and I basically chose a graph permissionally equivalent network. And yes, what I'm telling you today is the QM9 dataset that can be learned well too. I did not have too much success with this. Like too much, like proper success would be to also be able to predict some of the physical properties. Like there is some homolumograph, like there's some other physical properties that is here. I'm still trying to train them, and that is a classical problem. Like you cannot always have a network that will train. It's a question of finding the network. Then you try to come up with a cleverer and cleverer ansatz or a different network till you can find maybe something that can be trained right, um, and you succeed with the learning task. So for me, I think the problem starts with successful training and training against an unknown problem, unknown data, like how well it generalizes. So basically, what I learned about molecular problems is uh, to have a better chance of succeeding, you want to start with a problem that has coordinates, a problem that is geometric. Because geometric means you have the SO3 Lie algebra in it anyways, you can just simply pick an encoding that will be equivariant and you can keep that. Second, something helps a lot is putting the problem on a graph. And like uh, on the archive paper I presented, like if you put it on a graph, then there is a question of cleverly choosing your node features, edge features. Sometimes it's possible that the training would become easier or training would become possible. And yeah, that's how I'm trying to work on the QM9 dataset now. Um, Thanks for listening. I hope that there was something interesting for you to hear. Um, if you
Right?
are an expert, yeah, if you're an expert of quantum machine learning, maybe it was not too new. I don't know. But yeah, do you have any questions? Please, I'm happy to take questions.
Okay, great. Thanks, Samia. Thanks for the great presentation. Let's see if we have any questions. Does any of you would like to ask? I will check the comments because there were some interesting comments um, on our chat. Okay. Yeah, there was a comment. This is one of the best session on symmetries, equivariance, and their permutations. Um, there was a question whether it uh, works for NO3 ions. It was already some time ago, so I'm not sure to
I'm
which
sorry.
slide it was related. It was asked by Dave, so Dave, maybe you can unmute and ask.
Yeah, the the, um, the question involves nitrate ion, and unlike ammonia, which is a non-planar molecule, nitrate is all in the same plane, but it does have a non-trivial electronic structure. And I was wondering if you were to do the same graphic methodology to produce the the setup, would that work? Or I assume you haven't tried it yet, but I was interested in your thoughts on this.
Yeah, a great question. So nitride is not also not coplanar, right?
Well, yeah, I mean, NH3, because of the unpaired electrons, I mean, there's a
Yes.
picture there, is not coplanar, whereas NO3 is coplanar, and it has a non-trivial resonance electronic structure. Um, but in a naive sense, you can just say, well, we don't have to pay too much attention to what the electrons are doing. We're more interested in the question of just what are the vibration modes of this thing. So that
Yeah, actually, this may be a very good thing to try. So, like I showed you in the talk, the putting it on graph works more when you have a richer geometry. So it worked better for ammonia molecule than it worked for lithium hydride. Now, if you give me a data set with the coordinates, then we just have to see. It would work better than lithium hydride for sure, but how does it compare with ammonia? Yeah, this could be an interesting thing to try.
yeah, I mean, lithium hydride and molecules like N2 are the symmetry makes it a lot easier on a computational point of view, but I'm not convinced you're going to learn a lot. I mean, I'm looking at this though, and I'm thinking, well, how far away are we from being able to obtain a quantum computer that will do a good simulation of NH3.
I see. Um, yeah. Uh, right now, I think I just try to address the question of generalizability.
Right.
So, in that sense, ammonia was like a perfect example because of the rich geometry. The graph method worked very well.
Mhm.
Yeah, but yeah, I guess it's an open question. Like, are you thinking of like a circuit simulation, like with the Hamiltonian?
Well, actually, I'm thinking of something like a Hamiltonian. I don't know if I could
Mhm.
characterize that as a circuit. Um, my interest in this is far away from being practical. I've been looking at the questions of if you have, say, a platinum atom that's floating in space, um, how many qubits do you need to simulate the outer electrons of that? And then if you bring together some number of platinum atoms, how long before it stops behaving like individual atoms and starts behaving like a piece of metal? Uh, and in particular, the question is, what is the minimum number of platinum atoms such that you'll be able to get a metallic behavior and start to get insight into platinum catalytic activity? And
I
this
see.
is everybody's favorite catalytic reaction. N2 plus 3H2 goes to ammonia. Um, and my preliminary conclusion is that 32 platinum atoms is the absolute minimum number. Um, Whether that's adequate for simulation, I don't know yet. And I'd say we're probably decades away from having quantum computers that can run the thing. But I'm confident that anything less than 32 platinum atoms would not be adequate. So that's where I'm coming from. Kind of not directly relevant to your work, but it's still I find your work to be interesting because you're showing a path to reducing the number of qubits that are required for a given system model.
Um, yeah. So that just comes from actually trying the problem out. It looks like qubits have good expressivity. I mean, something like we need very much fewer parameters if you're using the qubit system compared to maybe convolutional neural network or something. Yeah, but that's for a learning problem. Um, but this is still interesting. Like the expressivity is quite good with 4 qubits, 6 qubits, 8, 10 layers. Yeah, it worked very well. That's good. And yeah, yeah, your question is also very interesting. I don't know how to begin, like simulating 32 platinum atoms.
Oh, it's non-trivial. There's all kinds of
Yes,
unfilled
yes.
p orbitals and crazy stuff like
Mhm.
that.
Okay, good. Thanks, Dave. I see that Ron would like to ask a question. Before that, I want to tell you that I will need to leave soon in a few minutes, so Helen and Deb will take over the further moderation. But I already would like to thank everyone and thank Samia once again for the great presentation and discussions. And Ron, you can ask your question now.
Thank you also for moderating.
Thanks, so please,
Uh,
Ron. Mhm.
Thank you. So in your QML experiments, just uh, want to try to understand, were you using like a traditional ML stack where one or more of the layers are replaced by a quantum circuit? Is that how that goes? And were you using the quantum circuits at the front, at the top of the stack, or somewhere in the middle?
The Stack is completely quantum circuits. It was done with Penny Lane. And did I use some? Okay, I know like slide 2 or 3 is like the circuit.
Okay, so that's very interesting to me. All of the layers were quantum circuits via simulator.
Yeah, so okay, the paper I took it from by his colleague, that's also, I think, referenced somewhere later. Basically, this is the answer. And this works great. Like if you choose this UX, this particular encoding, this gives you rotational equivariance and a bit of permutational equivariance too. But this is the way you want to take your data, some parameters, alternately you apply on your initial state, which is in equation 2.
So you're repeating this alternation a
Yeah,
certain number of times. Okay.
yes, using an
And
embedding.
again, the parameters are just parameters to rotational gates.
Yes.
Yeah. All right. Great. Thanks. I don't think I've ever seen it where it's all quantum. I've usually seen QML stuff where there's at least one classical layer in there.
Um,
Maybe it's on the output or something. I don't know.
yes,
But
yes, yes.
thank
I
you.
mean,
Thank you.
yeah. So the optimizer is always classical. I mean, there is no way of doing it quantum mechanically, I think. Yeah, that's the output layer. Yes.
Okay. Thank you.
Okay, good. Do we have more questions? Soumya? Okay, I do not see more questions now, so I think we can finish for today. So Samya, thank you once again. Thanks for the great presentation. Thanks for answering the questions. So I believe that we learned a lot and we'll try to upload a video recording to our YouTube, or Helen can maybe tell more about it. I believe that it's already live streamed, right? Yes. Okay, great.
Thank you
So,
for
yes,
the opportunity again. Anybody who wants to talk to me, just shoot me an email.
Oh, you
Thanks
are
for
welcome to come back for next talk.
yes,
I
yeah,
will try to listen some of the ones. There are some interesting ones coming
yeah.
up. Yes.
There's the next one tomorrow. Good. Thank you once again. I need to leave, so Helen, I think you can also finish the recording, and yeah, we hope to meet you next time.
Okay. Thank you very much.
Thanks. Bye bye.
Bye bye.